All right, so let's get right into it. When we talk about making AI better, our first instinct is usually just build bigger models, right? More power. But what if the real secret, the real breakthrough, isn't about working harder, but working smarter? Like knowing when not to use all that power. That's exactly what we're digging into today. A really clever trick to make AI way more efficient. And it all comes down to a simple but powerful idea, a smart skip. And really, this is the fundamental question that gets the whole thing started. I mean, we've got these incredible AI models that can do amazing things up in the cloud. But how in the world do you cram that same level of intelligence onto a tiny low-powered chip? The kind you'd find in a drone, a smart camera, or maybe a small self-driving car? It's a total mismatch. These really complex AI models, especially for things like image recognition, are absolute gluttons for computing power. They're just so hungry for resources that these small embedded systems, they just don't have. So you're stuck, right? You either use a much dumber model or you figure out a way more efficient way to use the really smart one. And this leads us to a really elegant solution called the IDK Cascade. And yes, IDK literally stands for I don't know. The whole idea is to create a chain of AI models, starting with a simple, fast one and moving up to the complex, slow ones. So an image comes in and the simplest model takes a look. If it's confident about the answer, boom, we're done. Easy. But if it's not sure, it basically just says, I don't know, and passes the problem up the chain to the next, more powerful model. Okay, the best way to think about this is like triage in a hospital ER. It's a perfect analogy, right? You don't send every person with a sniffle straight to the head neurosurgeon. That would be insane. First, you see the triage nurse. That's our quick and dirty model. Classifier A. If they're stumped, okay, you get passed along to the doctor on duty. That's our more powerful classifier B. And only for the really tough, complex cases do they call in the top specialist, our biggest, baddest, most power-hungry model, classifier C. It's a brilliant way to save resources. So this cascade system is already a huge step forward. But then the researchers asked this really fantastic question. What if that first model, our triage nurse, sees a problem that's so obviously difficult that it just knows the next model in line, the general doctor, won't be able to solve it either? Could we save even more time by just skipping the middleman and going straight to the expert? And that led to the first attempt at this, something called threshold skipping. The logic here was super simple. If the first model's confidence in its own answer was crazy low, like, say, below a set number, a threshold of 0.3, that was a pretty good sign that this was a really hard problem. And if that happened, the system would just automatically skip the second model and punt the problem straight to the most powerful one. But, this simple approach, it had some pretty serious problems. It was kind of like using a sledgehammer to crack a nut. For one, it was only looking at a single signal, confidence, and not fixed number, that 0.3. It wasn't some magic number that worked for everything. It actually performed pretty badly on different kinds of data. So here's the kicker. If it made the wrong call and decided to skip when it shouldn't have, it could end up wasting a ton of time. So much so that sometimes it was even slower than if it had never skipped at all. And this is where the real breakthrough happens. The researchers figured out that the problem wasn't the idea of skipping. The idea was good. The problem was how that decision to skip was being made. The answer wasn't to just mess with the threshold. It was to make the whole decision-making process way, way smarter. So how would they do it? How do you make skipping smarter? Well, instead of just that simple if-then rule, they brought in another lightweight AI model, a random forest, to basically act as the traffic cop. You can think of it like a little committee making the decision. And this committee looks at 3 different signals from that first classifier. It doesn't just look at confidence. It also looks at something called entropy, which is a measure of its overall confusion, and its margin, which basically tells you how torn it is between its top 2 guesses. And this is the absolute key right here. The researchers themselves said it best. These 3 features together give you a much richer, more detailed picture of how uncertain the model actually is. It's like the difference between a doctor just shrugging and saying, I'm not sure, versus that doctor saying, okay, I'm not sure, and here are the 3 specific reasons why I'm having trouble with this diagnosis. It's a whole other level of insight. So, first up, the researchers tested this new random forest skipping on a big, powerful cloud computer, a Google Colab instance. And the results were fine. They were a bit mixed. There wasn't some huge, obvious winner. But that kind of makes sense, because on a supercomputer, the penalty for making a bad decision isn't that big. Everything is already super fast anyway. So this is the real question, isn't it? A giant cloud server doesn't have the same problems as a tiny chip in a drone. So what happens when you run this exact same test, but on hardware that actually mirrors the tough, resource-limited environment of a real-world device, an environment where every single millisecond is precious? So for the ultimate showdown, they moved the whole experiment over to an NVIDIA Jetson Nano. Now, this is a small, low-power computer on a chip. It's exactly the kind of thing you'd find in robotics or in small-scale self-driving cars. This is the real deal. This is where efficiency isn't just a nice little bonus, it's everything. The stakes just got a whole lot higher. So what happened? Let's look at the raw numbers. You can already see some pretty big differences here in the time it took to process just one image. But numbers on a table are one thing. To really feel the impact, let's see this visually. And whoa, look at these results. This is where it gets really dramatic. On the left, you've got our baseline, right? No skipping at all. That's about 1,630 milliseconds. Now look at the middle bar. That's our smart random forest skipping. It's the clear winner, bringing the time down to 1475. Nice. But then look at the bar on the right. Oh man, that's the old simple threshold method. It's an absolute disaster. We're talking over 2,100 milliseconds. It wasn't just a little bit slower. It was so much worse than just doing nothing at all. It actively hurt performance. That's just wild. So yeah, the conclusion here is just crystal clear. When you put it under the pressure of real-world hardware, that smarter random forest skipping method wasn't just a little better. It was the only one that actually helped. That old simple method just completely crumbled. Let's actually put a number on that victory. On this low-power chip, the smart skipping method was 9.5% faster than the standard Cascade, which was already pretty efficient to begin with. In the world of embedded systems, a 9.5% speedup is a huge deal. Every single percentage point counts. And this is why this all matters so much, way beyond some lab experiment. This isn't just a paper for academics. This is the kind of smart thinking that unlocks the next wave of AI on the gadgets we use every single day. It's how we get smarter AI into our cars, our drones, our homes. And it just goes to show that sometimes the biggest improvements don't come from more brute force power, but from being more intelligent about how you use the power you already have. It's all about bringing that amazing cloud-level AI down to earth. And that kind of leaves us with this one last really exciting thought. Work like this is just one more step towards a future where really powerful, instant AI isn't locked away in some massive data center, but it's just all around us in everything. So the real question is, what amazing new things are we going to create when every single device can think this fast?